Welcome to Lecture 2 of Module 8. We're moving on in the perturbation theory, and now we're going to be talking about second-order perturbation theory. We're simply extending the work that we did before on first-order perturbation theory to the next order. So there's actually a general formal technique that's used to determine perturbation theory to arbitrary order. It's kind of complicated and very formal. I'm not going to go through that here because we're not going to be developing perturbation theory out to high order. We're only going to go to second order and then we're going to stop. That's actually very common in undergraduate classes to do that. Our strategy then is going to be to calculate one more derivative beyond that Feynman-Hellmann theorem that we worked on before. And the idea is that we're going to set up our notation to remind you of that first derivative, and then we'll just take a derivative of that to get the second derivative, and then we'll get our goal. Now, note that this calculation is quite a bit harder than calculating the first derivative. First derivative only had 3 terms in it. This second derivative is going to have a lot more. To extend this to the third derivative, while in principle you could do this, I suspect you really wouldn't want to do it this way. And that's in part why there's this other formal way that it can be done in order to extend it. But it's still messy and hard no matter how you do it. So we're going to use lambda as our small parameter. Last time we used delta, but it's actually more common in the literature to use lambda. We're going to write our Hamiltonian as a function of lambda as equal to the unperturbed Hamiltonian, which we'll call h0, and then our perturbation, which is lambda times the operator that we're going to call v of x. The wave function that we're going to be working with is going to be denoted n of lambda, n being an index, or you can think of it as the principal quantum number, and the associated energy is En of lambda. And as I had said before, we're simply doing a Taylor series expansion of that energy function, En of lambda, as a function of lambda. So we're going to have an En of 0 plus lambda, the first derivative of En with respect to lambda, evaluated at lambda equals 0, plus lambda squared over 2 times the second derivative, evaluated at lambda equals 0, and so forth. And just to remind you in terms of the notation, En of 0 is just the eigenvalue that the eigenstate has with respect to h0, so I can think of that as the expectation value of bra n h0 ket n. The states n of lambda are eigenstates of h of lambda, so h of lambda acting on n of lambda is equal to En of lambda, n of lambda. And of course, I'm working in a situation where things are continuous. So as lambda goes to 0, n of lambda is going to approach this state n that has no lambda dependence to it whatsoever. And of course, we always work with normalized states. So n of lambda, the bra ket is equal to 1. Now, I'm going to just recall for you what we calculated previously for the first derivative. The Feynman-Hellmann theorem told us that we evaluate that by taking the first derivative of the Hamiltonian with respect to lambda. You look at the Hamiltonian, it's a linear function in lambda, so the first derivative is just equal to v, and so I'm just evaluating this expectation value, bra n v ket n, and we call that v underscore nn. That's just a notation, but you will find that compact notation is nicer to use than this bra n v of x operator ket n notation. Now, what we need to do is evaluate the second derivative. So I first want to remind you what that first derivative was before we threw out the terms whose first derivative vanished when lambda went to 0. So we actually had 3 terms. We have a derivative of the bra, we have a derivative of the Hamiltonian, and we have a derivative of the ket. When I take the second derivative, I now have to distribute a second derivative over all 3 of those terms, and it gets kind of complicated. But you see, I'll get a second derivative of the bra. I'll have a term that has a first derivative of the bra with a derivative of h. I'll have terms that have derivative of the bra, derivative of the ket. I'll have, second derivatives of the h, and so forth. There's a lot of different terms there. But here's what they are. I've grouped them all together. So I have a second derivative of the bra. I have a term that has the first derivative of the bra and a first derivative of the Hamiltonian. I have a term that has a first derivative of the bra and a first derivative of the ket. Both of those guys, there are 2 different ways that I can get those terms, so they each have a factor of 2 in front of them. I have the second derivative of the operator, sandwiched in a bra ket sandwich. I have two terms that involve a derivative of the Hamiltonian with a derivative of the ket, and I have a term that has the second derivative of the ket. So those are all of the terms. You should sit down carefully with a piece of paper and work them out. Those are all of the terms that contribute to the second derivative. And now I want to start rearranging them and throwing out the terms that are equal to 0. And we'll see a number of these terms are equal to 0. But you also can see it's a bit of a mess. And so you do have to be patient to work through this and think in our sort of French cooking style of how to do things in order to make your way through this kind of algebra. All right, first thing to notice, the operator is a linear operator in lambda. So when I take the second derivative, I get 0. So that term is gone. Second thing to notice is I have these three terms that involve second derivatives of the bra and the ket, or a single derivative of the bra and of the ket separately. What you can see is for the first term and the last term, that h of lambda can act against an n of lambda. And because it's an eigenstate, I can pull out an e of lambda. So I'm going to go ahead and do that. And I'm going to now, but I can't do that for that middle term, the term that is d by d lambda n of lambda h of lambda d by d lambda n of lambda, because h of lambda is not an eigenstate with respect to the derivative of a bra or a ket. So I'm going to use my add 0 trick. I'm going to add and subtract an en of 0. So I'll have the minus en of 0 in a term that I'm going to have to end up keeping. And then I have the plus en of 0 that I'm going to put in that first term that we've denoted in red. I'm going to factor out the en of 0. Now, if you look at that term in the parenthesis, that term in the parenthesis is the second derivative of the bra ket nn. So the bra ket nn, if I take the second derivative of that, that's what this expression is here. It's the second derivative of that. You can carefully go through and work that out. I need the factor of 2 in there in order to have it be the second derivative. But of course, we know that n of lambda is equal to 1. So its second derivative is equal to 0. So that term also gone. Now we're going to simplify dh d lambda. That just becomes v. So I can make that substitution in of the v. And there I have it. That's my simplification of the second derivative. We now have to figure out how to evaluate that, and that's going to require me to evaluate this derivative of the bra, and equivalently, I can get the derivative of the ket. To do that, we have to refer to the Schrodinger equation. So the Schrodinger equation is actually written for you in the second line. It says h of lambda acting on n of lambda is en of lambda times n of lambda. If I take a derivative with respect to lambda of that, I of course get the derivative hitting both of the terms on the left-hand side and both of the terms on the right-hand side. Now the derivative of h with respect to lambda, that's going to be b, and we know the derivative of en of lambda with respect to lambda, that ends up being vnn. And so we can replace both of those by v and vnn. And now what we're going to do is we're going to do some rearranging of things. We're going to first notice that the derivative with respect to lambda of n of lambda must be perpendicular to n of lambda, because n of lambda is a unit vector. If any part of that derivative was not perpendicular to lambda, lambda would not remain a unit vector. And this is true when the energy eigenvalue is non-degenerate. Things get more complicated when it's degenerate. I'm not going to go into the details of how that complication occurs, but things just get more complicated when it's degenerate. So we're going to assume that the energy eigenvalue n is non-degenerate, and then we're going to create a projection operator which says take the identity operator and subtract off the projection onto that initial state n ket n bra, and that's just equal to the sum of the projection operators m ket m bra for all m that are not equal to n. And the thing that is important about this is that this qn operator, when it acts on the state n, it gives 0, because it's the identity minus the projection onto the state n. And so you can just work that out quietly if you want to using the definition of the qn. You can verify that qn acting on the state n is equal to 0. But because the state d by d lambda of n of lambda is perpendicular to n, this qn projects me perpendicular to n. And so qn acting on that state is just equal to the state. I don't lose anything because I'm projecting onto all of the Hilbert space that's perpendicular to that one state n. Okay? Be sure you understand that. That's a subtle point. The Qn operator does not do anything to this derivative of the n of lambda ket. Okay? So that means I can multiply the Schrodinger equation that we have by a Qn. So I'm going to multiply by a Qn on both sides. Now, when the Qn acts on the n of lambda, that's going to get rid of it in the limit where lambda goes to 0. So we can get rid of that term. And I'm now going to do a rearrangement. I'm going to join together the term with the h0 and the term with the en, because they each involve a derivative of the ket n of lambda. So I'm going to bring those two terms together. And now I'm going to bring the term that has just the n of lambda, the qnv n of lambda. I'm going to bring that to the right-hand side. I get a minus sign when I do that. And now what I need to do is I would like to multiply by the inverse of the operator h0 minus en. Now, initially, when you think about it, that operator, h0 minus en doesn't have an inverse. Because when that operator acts on a state n, that operator is going to give, h0 is going to give me en times that state. So when that state h0 acts on the state n, it's going to give me en, and then en minus en is equal to 0. So there's a 0 eigenvalue of this operator, h0 minus en. But the qn projects me perpendicular to that space. So in the reduced subspace, that's one dimension smaller in the Hilbert space, I can invert that operator, qn h0 minus en. So I'm going to formally assume that I have the inversion of that operator, which I'm going to just write as qn times 1 over h0 minus en. And then I'm going to multiply both sides by that, and the qn 1 over h0 minus en times the qn h0 minus en, that's going to give me a 1, and it's multiplied by this d by d lambda of lambda n. And so I get now a formula for d by d lambda of n of lambda. And it's just equal to minus qn 1 over h0 minus en qn v n of lambda. Okay? Now, I already have the derivative calculated. The second derivative is calculated. It's sitting right above there for you. Now what I need to do is I need to substitute this result in to that result for the derivative of the ket and the derivative of the bra. I get the derivative of the bra just by taking the Hermitian conjugate. So let's go ahead and do that. We get 3 terms. So I have a d by d lambda of a bra. I have a term that has a d by d lambda of both a bra and a ket, and I have a term that's a d by d lambda of a ket. I'm going to substitute in for the d by d lambda in those 4 different places. The first term gives me minus 2n v q 1 over h minus e q v times the state n. I'm now setting lambda equals 0 after I've done the derivative. The middle term is a big term, but if you look carefully at that, and then the last term is the same as the first term. If I look at that middle term, however, you see I have a 1 over h0 minus en, and I have a h0 minus en. And because I have the q's in there, those are actually inverses of each other. So I can replace those by 1, and I get qn times qn. But qn is a projection operator, and you can work it out. Qn squared is equal to qn. So I can replace that with a qn. And now you see these two terms are exactly the same, but they have opposite signs. So they cancel each other out. They're gone, and I'm left with the second derivative. It's minus 2n v of x qn 1 over h0 minus en qn v of x n. And now if I substitute in what the qn is, it's a sum over m not equal to n of the bra-ket sandwich. I'm going to substitute that in. What you see you're going to get is we're going to get a matrix element vnm. The middle term is going to be an m bra 1 over h0 minus en and m prime ket. And I'm going to have a vm prime n on the other side. Notice that, again, you might think that that term, m 1 over h0 minus en m prime, that thing has an infinity in it. But remember, m can't equal n and m prime can't equal n, and it's non-degenerate. So there's no other eigenvalue that's equal to en. So that h0, when it acts on those bras and kets, will be perfectly well defined. So that operator is well defined. Okay? And because these states are eigenstates of the h0, I can just evaluate it. It's going to be an em minus en times a delta m prime, because the eigenstates are orthogonal to each other. I can use the delta function to get rid of the sum over m prime, And we now have our nice compact formula for the second derivative. Minus 2 the sum over m not equal to n, vmn squared divided by em minus en. And I'm going to just change the sign by changing the sign in the denominator, making it en minus em, and having a plus sign. So now I'm ready to substitute this into the Taylor series expansion. So we've now gotten our Taylor series expansion through second order of en of lambda, and it's en plus lambda vnn plus lambda squared, sum m not equal to n, vmn squared over en minus em plus a third order term. All right, now, because we've calculated this derivative of the ket n of lambda with respect to lambda, we can actually figure out what the wave function does as it changes. It's, of course, equal to the initial wave function n multiplied by lambda times this derivative. We can plug in what that derivative is. And so we get that the state n of lambda is equal to n plus lambda, sum m not equal to n, the ket m, vmn em minus en. And that's our expression for the wave function. Okay? So we've now gotten our perturbation theory done. Let's try to apply this to a problem. If you remember, we worked with a simple harmonic oscillator where we perturbed the spring constant. We set k goes to k plus lambda times k. And so that object multiplying lambda, that's my v of x. And the term without the lambda, that's my h0. We need to calculate these matrix elements. We calculated in the previous lecture what VNN was. We used the virial theorem to verify it's 1/2 h bar omega times n plus a half. We now need, and that's going to give me my first order correction. We now need to calculate the VMNs for arbitrary m and n. Well, n is the state that I'm looking at, but for arbitrary m, I'm going to rewrite the x in terms of a and a dagger. And when you do that, there's a term that involves the square root of h bar over m omega. But because it's it's x squared, I'm going to get the square of that constant. So I'm going to get an h bar over m omega. And then I get an a plus a dagger squared. Let's FOIL that out. I get an a squared plus a dagger plus a dagger squared. And now we just have to think very carefully. We know exactly what happens when an A operator acts on an N state and when an A dagger operator acts on an N state. So when the A operator acts on it, it gives a square root of N times an N minus 1. And if it acts a second time, I'll get a square root of N times a square root of N minus 1 times an N minus 2. And I can similarly work it out when an A and A dagger act and when an A dagger A act and when an A dagger squared acts. You can see in that first case with the A squared acting on the N, the state n goes to the state n minus 2. So only if the state m is equal to n minus 2 am I going to get a non-zero result. And indeed, when you work these out, I'm going to get one term that's a delta function where m is equal to n minus 2, and that's multiplied by square root of n times n minus 1. I'm going to get a term where the m and n are the same, and that's going to be multiplied by the square root of 2n plus 1. That corresponds to the a dagger a term plus the a dagger term. And then the a dagger squared term is going to give me a delta m equals n plus 2 times the square root of n plus 1 times the square root of n plus 2. Okay, now I have all of the VMNs, and I just substitute into the sum. Now you see, because m is not equal to n, that middle term is not going to contribute. And because I only have two other terms, that sum over an infinite number of terms is only going to actually have two separate contributions in it, when m is equal to n plus 2 and when m is equal to n minus 2. Okay, so we're going to go ahead and substitute that in. These are the two contributions. I get a h bar omega over 16 squared. That's because the VMN had a prefactor of h bar omega over 4. And then I have the square of the VMN, so I'm going to get the square of that n minus 1 is going to give me n times n minus 1. And then I have to look at the energy difference. In this case, the energy difference is going to be 2h bar omega. And then I'm going to have an n plus 1 times an n plus 2 when I square that square root. And now the energy difference is equal to minus 2h bar omega. So I'm going to get a minus sign in that contribution. We now expand out those numerators, and there is a huge cancellation that occurs. The n squared terms cancel. We find that that expression ends up being minus 4n plus 2. And so we can simplify that. I'm going to go back once again to let you see that again. There's a 4n plus 2 that comes out. I have a 1 over 2h bar omega. You see that h bar omega is going to cancel with the h bar omega squared in the numerator, leaving me an h bar omega. The 2 is going to cancel the 4n plus 2 and make it into a 2n plus 1. I'm going to borrow another 2 from the 1 over 16 to make it n plus a half. So I'll have an h bar omega times n plus a half times a lambda squared over 8. And indeed, that's what we get. There's a minus sign as well that comes out from that. Now you see I can factor out an h bar omega times n plus a half times all of those terms. So I'm going to go ahead and factor that out. And now I get a power series, 1 plus lambda over 2 minus lambda squared over 8 plus, we don't know yet what the next order term is, but if we extended the perturbation theory, we could work that out. And if you instead look at the Taylor series expansion of what the exact result is, which is h bar omega times, I'm sorry, there's a typo. There should be h bar omega times n plus a half times the square root of 1 plus lambda. You can see that square root of 1 plus lambda is exactly equal to 1 plus lambda over 2 minus lambda squared over 8 and so forth. And so you see it works. And of course, it's very comforting to see that it does work, that we're able to get an expansion for the energy in a power series in lambda, and that when we work it out in a detailed example, we get the exact result in a case where we could solve it exactly. So that should give you comfort that the whole technique works. And, is it complicated? Yes, I have to calculate all these VMN terms. I have an infinite sum unless that summation has a lot of terms that are 0 and so forth. So it is difficult to go through and tedious to go through these calculations and get it all the way to the end. But again, it is just French cooking. What we have here is a lot of simple rules that we have to evaluate and just put them all together. And we just have to be careful at how we put them together to make sure we don't make a mistake. So with that, I'm going to end lecture 2 of module 8 on second order perturbation theory.